The last little bit from Chapter 10 that I wanted to cover was the kinetic molecular theory. It's just a way of thinking about gases and how gases behave and helping us understand how gases behave. And it's just basically used to explain the behavior of gases as a collection of randomly moving molecules. Right, earlier we talked about pressure. And what exactly is pressure? Well, pressure is essentially, you want to think of all these molecules that are moving within the sample. Pressure is how hard are these molecules bouncing against the walls of their container. The higher the pressure, the harder those molecules are bouncing against the wall of the container. The lower the pressure, right, the opposite. Those molecules wouldn't be hitting the wall of the container as forcefully. So it also encompasses, right, that these molecules are moving and colliding with each other. And the wall of their container. And this assumes that we are working with gases that are ideal gases. So gases that do not show an intermolecular attraction or intermolecular forces, right? Any attractive or repulsive forces. So under ideal conditions. So we're assuming, right, that for this to be true, that the volume of the particles is incredibly small compared to how far apart they are. And that the particles are always moving, right? Some are moving quickly, some are moving very slow, but they're always in motion. There are no attractive forces or repulsive forces between those molecules, and that these collisions are elastic. That you think of, two pool balls bouncing together, two gas molecules are moving, they collide, and they elastically bounce off each other in the opposite direction. And that we can relate how fast they're moving, so the average kinetic energy of a sample, we can relate that to the temperature of a sample. And so here's the equation for our root mean squared speed that we're going to get to in a little bit. Basically, what it's talking about is this is the average molecular speed for a sample of molecules having an average molecular kinetic energy. And it's important because this ties in to our temperature and our molar mass of the gas. There are going to be two important variables in determining the root mean squared speed. So T is temp in Kelvin. R is our universal gas constant. Right, 0.0821 liters ATM mole Kelvin. And M of M is our molar mass of the gas. So this is important because let's think about how temperature changes and our root mean squared speed would change. Or let's think about how our molar mass and the root mean squared speed would change. Now remember that temperature is the average kinetic energy of the sample, where our kinetic energy is 1/2 mass times velocity squared. So if our kinetic energy, right, is a product of our temperature, the higher the temperature of the sample, the higher our average kinetic energy. The lower the temperature of the sample, or lower our average kinetic energy. So a sample that has a high temperature should have a high average kinetic energy. You'd expect that to have a large root mean squared speed, so moving very fast. Looking at the equation, right, temperature, if temperature was to increase, that number gets larger and larger and larger. Even if I divide by molar mass and take the square root, right, my root mean squared speed should also be increasing. So here are the two important components of our root mean squared speed. So I have this first graph. The first graph in blue is a sample of gas molecules of nitrogen. So it's all nitrogen, all the same molecular mass. I have that sample at 0 degrees Celsius. And so the important thing is about our temperature. Temperature is our average kinetic energy of a sample. So here's the sample at 0 degrees Celsius. So taking a look at the distribution of molecular speeds in the sample at 0 degrees Celsius, you see that I have a certain amount of the sample with low molecular speed. I've got a decent amount of the sample that's got a higher molecular speed, and even a very small amount of the sample has a very high molecular speed. I increase the temperature of that sample from 0 to 100 degrees Celsius. We see an increase in molecular speed, right? Temperature, as I increase temperature, I increase average kinetic energy. I'd expect to see an increase in the molecular speed as well. But within that sample at 100 degrees, and the sample at 100 degrees is the red curve, you still see that you have a certain population of molecules with a low molecular speed. Because again, temperature is the average kinetic energy. So we're still going to have a certain population of molecules with a low speed. We've shifted our average. Our average has now gotten a little bit higher, and you'll see at the higher end now we have a larger percentage of molecules with a larger molecular speed. So as temperature increases, our molecular speed will also increase. So as I increase the temperature of a gas, the gas molecules, the average kinetic energy is increasing, so the average molecular speed is increasing. Those molecules are moving more quickly within the sample. This distribution is now looking at different gases, but at the same temperature. So now all of these gases are at 25 degrees Celsius. I've got oxygen, nitrogen, water, helium, and hydrogen. So my question for you is, why, if I look at the molecular speed of these gases, why does hydrogen have the highest molecular speed at 25 degrees, and why does oxygen have the lowest molecular speed at 25 degrees? So if we think about our kinetic energy equals 1/2 mass times velocity squared. So these samples are all at the same temperature, which means they should have the same average kinetic energy. Well, we know oxygen is heavier than hydrogen, so my mass increases. In order for me to have the same average kinetic energy, if I've got a larger mass, I need a lower velocity. And I could say the opposite for hydrogen. Hydrogen has a lower mass, so in order for it to have the same average kinetic energy as oxygen, it would need to have a much larger velocity. So in terms of thinking about it as average kinetic energy, right, that makes sense. And in terms of looking at our equation for determining our root mean squared speed, right, down here we have our molecular mass. So obviously as this gets smaller and smaller and smaller, right, that root mean squared speed is going to get larger and larger and larger. Because I'm dividing by a smaller and smaller number. Because 3 is not changing, r is not changing, and temperature is not changing, but our molecular mass is. So that number gets smaller and smaller and smaller. The root mean squared speed is going to get larger and larger. So for a sample of gases, right, the lightest gas, the gas with the lowest molecular weight, would have the fastest, the highest root mean squared speed. So let's take a look at what this means for two properties of gases, diffusion and effusion. So diffusion we're familiar with, right? It's the ability of a gas to move through an area. And so, for example, someone walks into a room wearing a very strong smelling cologne or perfume, and a few minutes after they walk into the room, you smell that perfume. That's an example of diffusion. That gas molecule that was part of the perfume, right, worked its way across the room until you were able to smell that molecule. So it's just based on the random movements of a gas molecule from an area of high concentration to low concentration. To low. Right, an example being that we're all familiar with would be perfume moving through a room. And you might think that perfume moves straight through the room, right, from the person that brought it in to your nose and smelling that perfume, but it's actually not a straight line, right? Those gas molecules are moving and they're bouncing and bumping off of other gas molecules that are in the room. So they're literally playing bumper cars with other gas molecules, and so they're bouncing around, and eventually it reaches the other side of the room and you're able to smell or detect that molecule. That's different than effusion. Effusion is the ability of a gas to escape. The ability of a gas to escape through a membrane. So in this sample, it's still kind of like diffusion, that I need gas molecules to move. I need these gas molecules, right, to be bouncing off the walls, bouncing back and forth, bouncing off of each other. But eventually, I have one small opening in that chamber. Eventually, as those molecules bounce back and forth, right, they're going to find that opening and they're going to be able to escape from that chamber. That's effusion. And so as you'd imagine, as temperature increases, right, as temperature increases, my average kinetic energy increases, those molecules are moving faster. As they're moving faster, they're bouncing around, they're making more collisions, they're more likely to find that opening, and the rate of effusion would increase. So here's my question for you. I've got two balloons and they're filled with the same volume and they're at the same pressure and the same temperature. I've got one balloon filled with nitrogen and one balloon filled with helium. So here's my nitrogen and here's my helium. So the nitrogen balloon, that's resting on the ground because of a difference in density. Nitrogen is more dense than the average density of the air, whereas helium is less dense. That's why it's floating. That's not my question for you. My question for you is, I leave those two balloons for 48 hours after they were filled to the same volume and same pressure of two different gases. After 48 hours, the nitrogen balloon is approximately the same volume, whereas the helium balloon is about 1/4 the volume that it was 48 hours previously. So my question for you is, why is the helium-filled balloon smaller than the nitrogen-filled balloon? Why is that the case? Using our kinetic molecular theory and thinking about effusion, why would helium be a smaller balloon? Why would it have lost more of the gas than nitrogen after 48 hours? So the answer to that question is, thinking about our root mean squared speed, we already discussed that molecules of gas with lower molar mass, they're moving faster. They're going to have a higher root mean squared speed, right? To have the same average kinetic energy, they need to have a higher molecular speed. So helium is moving faster than nitrogen. Because helium is moving faster than nitrogen, it's going to have a lot more collisions, many more collisions with the surface of that balloon. Because it's going to have more collisions with the boundary of the balloon, it's going to have more chances to escape from the balloon. And that's why we see the helium balloon shrink over that 48-hour period of time. It's going to have a faster root mean squared speed, higher velocity. Because of that, more collisions with the balloon, and more chances to find that opening and escape from the balloon. So here's an example of how effusion was used during the Manhattan Project. So for the Manhattan Project, we needed to develop enrich uranium U-235 to greater than 5%. There are two naturally occurring isotopes of uranium, uranium-235 and uranium-238. Uranium-235 is the desired isotope that can support a nuclear chain reaction needed for nuclear fuel or for a nuclear weapon. Uranium-238, however, is the major isotope that's found. So how can we separate these two isotopes of uranium, right? They only differ by a mass of 3 AMU, an incredibly small amount. But we need to take this percentage from 0.72 all the way up to 5% of uranium-235. So actually, it was gaseous effusion that was used to separate these isotopes. So uranium hexafluoride was the only molecule that could be made with uranium that was slightly volatile. I think it turns into a gas at about 56 degrees. So if we look at uranium hexafluoride from the different isotopes, right, they differ in a molar mass of only 3 grams per mole. But that was enough, and so down in Oak Ridge, Tennessee, they literally just took this gaseous uranium hexafluoride and put it through round after round of this effusion. So just think of really long chambers, these really long chambers, and allowing that gas to effuse down the chamber. Because uranium-235 was the lighter version, that would effuse faster, slightly faster each round. And so just imagine tens of hundreds of rounds of this effusion. Each time, more of that uranium-235 is moving farther and effusing faster than the uranium-238, allowing you to enrich the uranium to a 5% or greater capacity. So the important thing from today's lecture, be able to use PV equals nRT, right? Be able to combine that with a balanced chemical equation to go from mass to moles to volume. Also be able to use PV equals nRT and the other variation that we looked at that incorporates molecular weight and mass of a sample. And just understand in general what root mean squared speed means for a collection of different gases at the same temperature or for the same gas at different temperatures. So just thinking about how as I increase temperature of a sample, right, I should increase my root mean squared speed. Or if I change the molecular weight of a gas, how that impacts my root mean squared speed. So on lecture on Wednesday, we're going to review for the final exam, and then on Thursday, we have the final exam.